All right. Well, thank you, Sasha. And you're not going to hear me talk about salt tectonics. Instead, I'm going to talk about really salt deposition and its relationship to rifting, specifically in the ocean-continent transition in the southern Gulf of Mexico. I'd like to start out by thanking TGS. Let me go to a pointer here. I want to thank TGS for the seismic data I'm going to show, and also the Institute of Tectonic Studies at the University of Texas at El Paso, who partly fund my research. So let's go to the Gulf of Mexico. This is the US coastline, Florida, coming around to Texas, into Mexico. And this is the Yucatan Peninsula down here and Yucatan Carbonate Platform. And it's a wedge-shaped ocean basin. It was Jim Pindell in his PhD who first suggested that it formed by the counterclockwise rotation of Yucatan about a pole near western Cuba, and that's held up over the decades. And that means it's bounded by a major transform fault near the east coast of Mexico here. And you can actually see the ridges and transforms. So the western GOM is dominated by large transform segments, whereas the eastern GOM is just Gulf of Mexico for those who don't know the slang. But the eastern GOM is dominated by ridge segments. And that's going to become important. I'm going to be talking about this area here in the southern Gulf of Mexico. And there are three main interpretations for what's happening in the ocean-continent transition. Jim Pindell and co-authors suggested that salt was deposited near sea level and then very late-synrift and then dropped really rapidly on the so-called outer marginal detachment, effectively a large rollover geometry with exhumation of subcontinental mantle in the footwall. Mike Hudek and Ian Norton actually divided the southern Gulf of Mexico into two salt subbasins separated by a basement high here, and that's basically off that corner of Yucatan. In the northern one, Yucatan subbasin, they said it was dominated by these so-called outer troughs, which basically looks like this down here. We'll come back to that. And whereas in the Campeche subbasin, they said there are no outer troughs, but there's actually an outer high along here. They also noted excess in this area back in here, excess supersalt extension, so upper Jurassic extension that can't be balanced by any known shortening or salt emplacement or anything like that. And we'll keep that in mind. And then I suggested things are actually more complicated rather than a simple subdivision like this. If you take map view, this would be rifted continental crust, this would be oceanic crust, that in parts of the GOM, namely the northeastern GOM, that would be dominated by ridge segments, most lines will cross that outer trough as part of the rifting. But in the western GOM, most lines will cross transform faults and you'll actually have an outer high. So it can be expected to jump back and forth. And that's what I wanted to test with these data. This is the data set from TGS, the Gigante data set. The map that you're seeing here, first of all, it's about 800 kilometers long. And it's a combined base salt and top oceanic crust. In other words, it's this red horizon along here. And then I also am going to show two boundaries. I did some others, but there's going to be the inner edge of the outer trough. That's going to be shown with solid lines and arrows. So that's this. And then the limit of oceanic crust will be shown with dashed lines and arrows right here. And we'll take a look at that first on three lines. That's all I have time for. One way to the northeast and then two down here in Campeche. And the data, again, are from TGS. They're 2D depth migrated data. So really nice data, dense grid, but they're not 3D admittedly. The vertical exaggeration that I'll show is always 2.5 to 1. So the scale bar is 10 kilometers. And if you rotate it to vertical, it would be 4 kilometers in depth. This is the line to the north. You can actually see the top and the base of salt very nicely. It's a relatively unfaulted base salt. And then suddenly this is the outer trough, and you'll see it's right where the moho comes up. Rather interesting. So I'm not really going to focus on the crustal architecture at all. I'm focused on that base salt and oceanic crust. And that's really all I'm going for. So here is that inner edge of the outer trough, which you'll see on a map in a few moments. And then here's that limit of oceanic crust. And that's on any given line, it's tough, but you tie it around in 3D and you get your best interpretation. Whether there's actually mantle exhumed right here beneath the salt or not, can't tell. All right, now we step far to the south and you'll see that there is no outer trough. The base of salt is effectively unfaulted and smooth. There are some velocity artifacts here. And the salt is perched above the level of oceanic crust. Some interesting crustal geometries down in here. Again, not talking about that. Now you go just a little bit farther to the southwest, and we're back to a nicely defined outer trough. And you can see there's the top Cretaceous coming through here, and it and everything else drops because the salt was thicker in this trough, depositionally thicker. So again, those two lines. All right, well, let's get to the meat of it. There are lots of examples, but that's all I can show. This is that map. Again, it's a map on the combination of the base of the in-place depositional salt, not a Lochthana salt, and the top of oceanic crust. The dotted black line is the limit of oceanic crust, and then the solid black line is the inner edge of the outer trough. And this is that corner of the carbonate platform and of Yucatan here, and this is that boundary from Hudeck and Norton, suggesting two sub-basins. Well, first of all, you'll see there is no basement high. This was one salt basin, plain and simple. But they were right in the sense that the Yucatan sub-area is dominated by outer troughs, as you can see between these two lines, but not completely. If you took a line through there or lines through here, you'd have an outer high. And the Campeche area, yes, there are lots of outer highs, as you can see, but there are discrete outer lows. And I've mapped areas just down in here in 3D, the same features, and you can see it. So this is a consistent pattern as you come into Campeche. Now, there are different trends of transforms and transfer faults, and I show them in these gray lines. There is a trend that is more north-northwest, south-southeast, that's shown in the dark gray. And then there's a trend that's more north-south, shown in the light gray. And what it does is suggests that there was a shift in the pole of rotation during rifting and during early spreading. Notice that the patterns don't shift gradually along strike as you would get with a nearby pole. There are these just abrupt jumps in the patterns. I should also mention that neither of these trends matches the known transform trends out in the deep Gulf of Mexico. So there's actually a third, or a second, I should say, shift in the pole, so 3 poles. And that's something Jim Pindel's talked about using gravity data here to show there was an early stage and then what we see out in the oceanic crust. And I'm adding one more shift. So I've segmented, or I've divided this margin, these 800 kilometers up. And you'll see that in this area that both the transfer faults and the transforms have the same north-northwest trend, whereas in 2 and 4, they both have the same north-south trend. But interestingly, segment 3, the inner edge of the outer trough has the north-northwest trend, and the transform faults have the north-south trend. Interestingly, there's a beautiful correlation with that excess supersalt extension. This is where it was mapped out by a student, Steyer, working with Paul Mann. And he just mapped out that there was excess supersalt thin-skinned extension here and here. This was the edge of his data, but not in here. And that matches beautifully the two areas where both trends are north-south and not this one. And I've looked at this and I agree with what they saw. So that's an important message right there. Something's going on that excess extension is telling us. So let's look at timing. Generally, people assume that there was a younging of extension towards the east. It's a wedge-shaped salt basin. Pindel has said it. Rob Pascoe said it. I've said it. Now, I'm going to assume that north-northwest trend predates this north-south trend. Very simply for 2 reasons. One, because it dominates in the southwest, whereas the north-south trend dominates in the east, where rifting was later, but also because of this area. And if we assume, which I think is entirely reasonable, that the opening of the outer trough, which is crustal rifting, predated spreading, then this north-northwest trend predated the north-south trend. In other words, the switch in pole of rotation happened during the formation of the outer trough. That's very reminiscent of the Red Sea, as many of you will know, where there are these localized deeps, like the Thetis Deep is where there's active spreading going on, but they're separated by areas of ongoing crustal extension. So although there's a gradual younging to the northwest of the onset of spreading, there are distinct spreading nuclei that later get linked by axial propagation. I would argue this is exactly what we're seeing in the Gulf of Mexico. You just have to flip this figure around so that on the west would be ongoing spreading, whereas in the east, you're getting pockets of spreading starting with the later get linked by axial propagation.
10 minutes, Mark.
Okay, thank you. Well, this is the whole story's in this figure right here. Let me explain this. This is from southwest to northeast with my 4 segments. This is relative time. It's also variable. I don't have any age control in here in terms of the specifics. I'm showing the 3 poles of rotation with the 2 time of switching. This would be the one out in the central GOM. We won't worry about that one. And then what I'm showing is with the blue line, the initiation of the outer trough. And again, this is schematic. And with the red, the onset of spreading. We know that they both predated the switch in poles in this segment, and they postdated the switch in poles in these 2 segments, whereas in segment 3, this happened prior to the switch, and the onset of spreading was later. Now, if we assume that evaporite deposition was coeval, and I think that's largely fair, but not in the details, then let's just put that in here. And what it means is the salt was deposited during the formation of the outer trough in these 2 segments, but prior to the outer trough formation in these segments. So what that means is after salt deposition and burial, there was ongoing crustal extension. And so there was matching thin-skinned extension that was decoupled from the pre-salt rifting by the salt. Classic salt tectonics. So just to sum up here, what I've tried to show you is the GOM is the conjugate margins, and you do see this also in the north, are dominated by ridge segments to the east and transform segments to the west. And that means there are more outer troughs to the east and more outer highs to the west, but it's not that simple because of that smaller scale segmentation. And those outer troughs, they say, did form along the ridge segments and the highs along the transforms. There are these 2 different trends suggesting a switch in the pole of rotation, but there are these complex timing patterns. And although there is gradual younging to the northeast, there are these distinct nuclei linked later by axial propagation. And coming into the salt, again, it's syntectonic. It was deposited during the rifting that created the outer trough in segments 1 and 3, generally to the southwest, but it was deposited prior to outer trough formation in segments 2 and 4. So as the trough formed, the salt flowed into the trough, and you had to have coeval extension above the salt in the sediment that was being buried, and that's what gives you that upper Jurassic supersalt extension. The results have implicated, well, actually, yes, you can see the same thing in at least one other place. I've seen it in a couple. This is a paper that's currently in review in Marine and Petroleum Geology by Marie-Eva Epin. I'm working with John Retto Manetshal, who's here in the audience. And it's based on some really beautiful 3D data from CGG in South Gabon. And you can see the same thing where there's a smooth base salt, then there's the outer trough right where the moho comes up in both directions. This is actually a propagator, so it's a little complicated, and there's a shift to what's happening out here. But they also have evidence for supersalt extension that is probably rift related, showing, because this is also where the timing of onset of opening of the oceanic crust was later in the north of this margin. So we think this is really exciting, pursuing this in some other basins, and I will leave it with that. And for those who are interested, this is from a salt mine in the Ural Mountains in Russia. Thank you.
Thanks a lot, Mark. We have a bit of time for questions. Anybody wants to go first?
Stop sharing.
Suzanne has a Q in the chat. Go ahead.
Hi, Mark. Thanks a lot for this. It's very inspiring. I was wondering a bit about, so you have all these transform and transfer fault trends. So does the salt in any way react to this? Because you would expect some strike-slip movement along it, right?
Yeah, so of course, again, it's going to depend on the timing of that pre-salt rifting and those transfer faults and what's going on above the salt. So the main thing is we start gravity gliding right after the salt is deposited. But in this area, in that northeastern area, it's also some thick-skinned decoupled extension. And so, yes, you might have, that. By the way, I didn't point out, there's also a correlation between the location of major diapirs and those troughs. So the salt was depositionally thicker there, and that definitely impacted the onset of diapirism. But it was probably, it's hard to separate that control out from the gravity-driven control, and I haven't tried to do that.
Yeah, I understand. That's pretty complicated. Thanks.
Generator raised the hand.
Yeah, I have a question about the Pindel's model and the question about the vertical movements and about the requirement to have very fast movements. If I understand well, in your model, it's a little bit more complicated because you might not have the salt at the same type of structure. So how yeah, go ahead.
Yeah, I would make two comments. And one is that, first of all, the geometries you see on the seismic data, and I've looked at 3D data that show the same thing in the northeastern GOM and the southern GOM, in the Kwanzaa Basin, in Gabon, et cetera. The geometries simply don't fit, in my opinion, that model the outer marginal detachment. We also don't see, so that's one issue. But the other problem, and this is related to, is where the salt was deposited. In their model, it was deposited near sea level, and there's this almost instantaneous drop to around the level of oceanic crust. And yet there is no structural evidence for that whatsoever. If you're going to take the hanging wall of some fault system, the outer marginal detachment, and have it near sea level and drop it to around the level of oceanic crust, well, then the footwall had to be near sea level also. And yet there is no evidence for that whatsoever. So what I would argue is that the salt was not deposited at sea level. There was topographic relief in the salt basin. Whereas in the margin of the salt basin, it was deposited closer to sea level. In the deep centers, it was deposited down as much as 2 or even 2.5 kilometers in terms of the top of salt at any given time.
Thanks.